Okay, so this is for chapter 21, alpha carbon chemistry, enols and enolate. So do the usual homework. And the homework will be those questions in the textbook. All right, so in this chapter, we are going to study some of those chemical reactions happened in the alpha carbon in some of those compounds has the carbonyl. We use Greek letter to describe the proximity of carbon atom relative to the carbonyl group. So this carbonyl group, so the one next to the carbonyl carbon is alpha, and then the next one is beta, gamma, delta, and so on. This chapter will primarily explore reactions that are taking place at these alpha and alpha locations. Alpha protons are the proton attached to an alpha carbon, and so most reaction cover here proceed with the enols or enolate intermediate, and here is the enolate and has the enol. We can see when you have a carbonyl carbon group, we can see the catalytic acid base can help converting the carbonyl to the enols, or we can use a strong base to deprotonate this type of part of the molecule to produce the enolate. Once we have the enols or enolate, and some of those chemical reactions can happen, adding some of those X group on the alpha carbon. If in the presence of acid base, ketone or aldehyde exists in equilibrium with the enols, and here is the carbonyl, catalytic amount of acid or base can convert the carbonyl to the enols. Enol is those kind of functional group has OH attached to a carbon. The carbon is in the CC double bond. The ketone and enol are tautomers of one another, and here we can see in this example for the cyclohexenol, 99% of the component exists at room temperature will be the ketones, and only small percent of enols. Usually, the equilibrium favors the ketones. There are exceptions, as the example below. The enol form is favored in the equilibrium, and here is the diketone, and you can see at the equilibrium, 70 to 90% is enols. The enol of 1,3-diketone is stabilized by conjugation and intramolecular H bonding. It is more stable than the typical enols and is favored at equilibrium. So this is the the hydrogen bonding inside the molecule. Phenol is an example where the enol is vastly favored over the ketone at equilibrium. And again, you can see the phenol is kind type of the enols because the hydroxyl group is connecting to the carbon C, and the C is in the double bond. Phenol is an enol with aromatic stability. The mechanism for the tautomerization depends on whether it is acid catalyzed or base catalyzed. And here is the mechanism for the acid catalyzed. So we're starting with the carbonyl. We have acid. So acid will protonate the carbonyl oxygen. And then this intermediate is resonance stabilized cation. And then we can use water. There's plenty of water to abstract the H plus and produce this enol. In the condition of base, so we have this alpha hydrogen, and then the base can take this hydrogen away and will produce this negative ion in the carbon and carbonyl, and then this is also resonance stabilized. So this is called the enolate. And so then if the base is not strong, then we will see the it converting into the enols by abstract the enolate abstract the H proton from the water. So the final is enols. So we're starting with carbonyl and can tautomerize to the enols. It is safe to assume that some fraction of the ketone aldehyde in solution will exist in the enol form. The alpha position in an enol is nucleophilic, because it has a partial negative charge electron rich. In the presence of strong base, an enolate will forms. So here we will use a strong base and starting with the carbonyl, and that carbonyl group has alpha H. So a strong base can just take that H away and will produce this enolate. The enolate is much more nucleophilic than the enols. It is as it carries an overall negative charge. So the enolate can undergo carbon attack or oxygen attack. So if undergoes carbon attack and that electrophile will adding onto this alpha carbon. If under oxygen attack, the electrophile will adding onto the oxygen. Enolate generally undergoes carbon attack, which is drawn one of the two ways depending on which resonance form of the enolate is used. So when we are using this form, we think of the double bond attacking the electrophile and the electrophile adding to the carbon, or we can say explicitly the negative charge on the carbon. So either this way or this way, but the final product are the same. Most of the reaction in this chapter will involve the enolate. So the enolate can be written in this way or that way. Alpha protons are the only acidic proton and on an aldehyde ketone that can be removed to form an enolate. When you have the beta gamma, they are too far away from the carbonyl, so usually we don't think they are acidic enough to be taken away by some of those strong base. The beta or gamma proton are not acidic. Deprotonation will not yield a resonance stabilized intermediate. The pKa value of the alpha proton must be considered when choosing the appropriate base to form the enolate. And here are a few pKa for the alpha proton: acetone pKa 19.2, acetophenone 18.3, and acetaldehyde is 16.7. And so this column show you how we see the structure of the resulting enolate or the conjugate base. They can be stabilized by the resonance structure. So here are the resonance structures. When pK value of the base and the enolate are similar, both product and reactant are present in a significant amount. For example, we have this acetaldehyde, pKa 16.7, and use ethoxide. So ethoxide becomes the ethanol, the pKa for ethanol 15.9, comparable with pKa for this acetaldehyde. So therefore, the equilibrium, even though the equilibrium still favors the weaker acid, the left side, but it's, the enolate can exist in significant amount. Yeah, so when the alkoxide is used, the enolate nucleophile can react with the ketone electrophile, and we'll see that in section 3 of this chapter. To irreversibly and completely form an enolate, a stronger base must be used, like NaH, sodium hydride, or LDA. Well, let's first take a look at using the hydride. So hydride is the H negative ion, and just abstract the H from the alpha carbon, produce the hydrogen gas and the enolate. LDA is a strong base commonly used to form enolate irreversibly. It is made by treating diisopropylamine with N-butyl lithium. So here is the process of produces LDA, lithium diisopropylamate. So that's LDA. It's a very strong base, powerfully strong base. So when LDA is used to form an enolate, the amount of ketone present at equilibrium is negligible. We're starting with this ketone or aldehyde. Starting with this acetaldehyde using the LDA, the very strong bulky base, and we can see that will abstract the H from the acid, produce this enolate, and then the conjugate acid. LDA features two bulky isopropyl group, which allows it to be a strong base, but not a good nucleophile. And that's for avoiding this strong base to attack the carbonyl carbon. When protons are alpha to two carbonyl groups, they are much more acidic. So here is a comparison. These two alpha hydrogen are adjacent to two carbonyl. And then you can see the pKa getting much smaller, which means the acidity of the two H is much stronger than this H. The increased acidity is due to increased stability of the resulting enolate, which is the conjugate base. And you can see this, there are three resonance factors, which means this negative charge can be delocalized over all these 5 atoms. 1,3-dicarbonyl are acidic enough to be irreversibly deprotonated by alcohol site. So if you have this kind of alpha carbon that are adjacent to two carbonyl, we even can use the ethoxide to completely remove the H, produce explicitly the enolate. There will be no need to use NaH or LDA to form enolate of 1,3-dicarbonyl. So this is one example of 1,3-dicarbonyl. 1,3 just relative location, so 1, 2, 3. It will be overkill to use NaH or LDA. Ethoxide will be enough. It is important to know what base to use in order to generate an enolate depending on the carbonyl compound and the desired result, reversible or irreversible. So here are some examples. So we have this acetone, and we want to partially produce enolate. We can use hydroxide or sodium ethoxide. Both enolate and ketone are present at equilibrium. But if we want to completely convert acetone to enolate, we can use sodium hydride or LDA. Then we don't have any ketone in the product. Here we have a 1,3 those dicarbonyl compound. We don't even need to use LDA, those kind of strong base that are overkill. Just use simple sodium hydroxide or sodium sulfide, we can completely converting those alpha carbon into the enolate, nearly completely enolated formations. Under acidic condition, ketone aldehyde undergo alpha halogenation. So here is the overall reaction with acidic condition Br2. Use Br2, then we can see the halogenation on the alpha carbon. It works for Cl2, Br2, and I2 not fluorine. The acidic condition means an enol is the reactive intermediate, and here is the mechanism. Part there are two parts. Part one is the enol formation. At acidic condition, we form the enols, which is this part, and the enol will have the reactions with Br2. So first part is the nucleophilic addition. The enol function as a nucleophile and attack molecular bromine. Then the second step is proton transfer. A proton is removed to afford the product, which is the halogenated ketones. In the halogenation on the alpha carbon. When unsymmetrical ketone is used, halogenation occurs faster at the more substituted carbon. Here, this carbonyl has two alpha carbon. This one is more substituted, and then the halogenation will be on this more substituted. So this carbon is kind of a tertiary carbon. That carbon is the secondary carbon. Yeah, the metal product results from more stable, more substituted enol. So this will be the intermediate, more substituted enol, and more stable. This enol is less substituted. What that means is you compare this carbon in the CC double bond and how many H is replaced by alkyl group. So here all the 4H is replaced by the alkyl or some other atom, and here there's one hydrogen, this hydrogen left over, so it's less substituted. Alpha hydrogenation provides a two-step synthesis for the synthesis of alpha beta unsaturated ketone. So here is a ketone, and you want to produce this alpha and beta unsaturated ketone. You can do like a two-step synthesis. First step is hydrogenate using acidic condition Br2 to put a Br in this part, then use some of those base to have the elimination reaction to produce another double bond. Other bases can be used for the elimination. So here in this example is using pyridine. Other bases can be T-butyl oxide, or say here the potassium T-butyl oxide, or even like lithium carbonate. Here, Warhag-Zelinsky H with Z reaction brominates the alpha carbon of carboxylic acid. So carboxylic acid has the OH group, has the kind of a special carbonyl. So you want to hydrogenate or brominate this alpha carbon, you have to use this special process called the H with Z reactions. So the first step is using Br2 in the presence of PBr3, then use water to finish the process. The mechanism is believed to be the following sequence. We start with carboxylic acid, and PBr3 will replace the hydroxyl by the Br. So it's acid halide. Acid halide can also have the enol form, and then that enol will acting as a nucleophile and attack the Br2, so that Br2 will be substitute one of the H in the enol, and finally produce this product. The final step is this type of acid halide hydrolyzed by water to recover the acid. The alpha hydrogenation can also be achieved under basic conditions, and so here is a ketone, and obviously here this left alpha carbon don't have hydrogen, so we will see the reaction happen on the right carbon. On the basic condition, I enolated the reactive intermediate. So to produce enolate, we need to have an alpha hydrogen. So therefore, the base will abstract this hydrogen from the alpha carbon, produce this enolate, and enolate acting as a nucleophile to attack the Br2 and finally produce this product. On the basic condition, polyhydrogenation typically results. So you can see here the same reactant as in the last slide, but we use the basic condition, and there are two alpha hydrogen, so then both alpha hydrogen can be replaced by the Br atom. Once the ketone is brominated, it forms an enolate, and bromination again at an even faster rate. On the basic condition, methyl ketone are converted to carboxylic acid using excess hydrogen and hydroxide. This is called the haloform reaction. So there are two steps. The first step is the basic condition with Br2, so they will become completely like a carbon connecting to 3Br, then that will become a good linear group replaced by OH. After all the three alpha proton are replaced, the CBr3 acting as a good linear group and extra substitution occurs. So here again, we first brominate this alpha carbon, and then we'll have the nucleophilic substitution. So this is two steps. The resulting carboxylic acid is deprotonated under the basic condition. This forces reaction to be completion. Once we finish the reaction, then we protonate this anion to produce acid. Br2, Cl2, and I2 can be used. This is a synthetically useful way to produce carboxylic acid from methyl ketones. Works best if the alpha of the other alpha carbon has no alpha protons. Recall that when an aldehyde is treated with hydroxide or alkoxide, an equilibrium forms where a significant amount of both enolate and aldehyde present. If the enolate attack the aldehyde, aldol reaction occurs. So this is we see there's acetaldehyde in the presence of base. It produces compound, and this is called the aldol addition product. The product filters both aldehyde and alcohol, so aldehyde and alcohol. That's the name, aldol additions. Note the location of the hydroxide group is on the beta carbon. So this alpha and beta, but this actually comes from the carbonyl. This beta carbon is the carbonyl carbon of the other acetaldehyde, as you can see from this mechanism. So the first step on the basic condition is the proton transfer. The alpha position is deprotonated to form an enolate. The enolate serves as a nucleophile and attack the other aldehyde and push the double bond onto the oxygen, produce this native ion. So then this resulting alkoxide ion is protonated to give the product. So therefore, this OH right now in this product is beta location, but actually this OH comes from this carbon. This carbon was this carbon, so this carbonyl carbon. The aldol addition is an equilibrium process for most simple aldehyde. Aldol product is favored, and here is another aldehyde on the basic condition. It favors the aldol addition. So you can think of the similar process for most ketone aldol product is not favored. The reverse process is called the retro aldol reaction. The mechanism is simply the reverse of aldol reaction. Right, so we see this product on the last slide, and we can see how this product decomposes to produce the starting acetones. So first step is proton transfer. The beta hydroxyl group is deprotonated, and the carbonyl group is reformed, expelling an enolate and leading group, and would recover in this step acetone. Then this enolate protonated produce another acetone. When an aldol product is heated under acidic or basic condition, an alpha beta unsaturated carbonyl forms. So this is for the aldol condensation, and we see this product before. It comes from the aldol reaction of two acetaldehyde. Once we have this product, if we heating the product, then it dehydrated, loss of water, produces aldol condensation product. The aldol condensation occurs when an aldol addition is performed at elevated temperature. So again, to summarize, this process produces aldol condensation product. Again, we can starting with acetaldehyde on the basic condition. Now notice here the condition is also heat. Then we can see the aldol condensation product, which is alpha beta unsaturated carbonyl. Aldol condensation occurs when aldol addition is performed at elevated temperature as compared. We can see this acetaldehyde do the aldol reaction, produces beta hydroxyl aldehyde. Then when heated, it will become the alpha beta unsaturated aldehyde. Or we can just do one step aldol condensation at elevated temperature. So this aldehyde condensation mechanism, just two parts. Part one, the aldehyde addition. Again, we use this acetaldehyde as example. So first step to process the aldehyde addition is the deprotonation of the alpha position. And then we have the enolate. Enolate acting as a nucleophile, attack the aldehyde, and then produce this alkoxide. Alkoxide get protonated, produces beta hydroxyl aldehyde. And then this beta hydroxyl aldehyde at high temperature dehydrate. So the first step on the basic condition is deprotonate this alpha hydrogen produces enolate, and then the hydroxide is ejected to form the product. So that's the step two. When two sterol isomeric pair bond can be formed, the product with fewer steric interaction is the major product. So here we have this alpha beta unsaturated carbonyl come from the aldehyde condensation reaction, and this double bond can have those stereoisomers, can be the cis or trans or E or Z. So usually the trans isomer is more stable because there is less steric interaction and also less electron repulsions. Because aldehyde condensation is favored, often it is impossible to isolate aldehyde addition product. So here is another reaction. This just aldehyde addition usually difficult to isolate. Even vapor temperature can induce the condensation. So this is the aldehyde addition condensation. The yield for condensation are typically much greater than yield for the addition reaction. So here we can try to control, we don't want to have the condensation at a lower temperature, that's 20%. And we elevate the temperature to 100 degrees to produce the condensation product that is 90%. Two different aldehyde and ketones reacting in a cross aldehyde reactions or mixed aldehyde reactions. So that will give you a lot of possible products. Here are two examples of aldehyde at basic condition. And we can have the acetaldehyde with acetaldehyde go through the aldehyde reaction, or we can have this the second aldehyde go through the aldehyde reactions, or we can have the mix of these two aldehyde, depending on which one we use as enolate. So this is using this one as enolate, and the last one is using that one as enolate. Cross aldehyde reactions are only practical if the number of products can minimize, which is achieved in one of the two ways. One of the substrates is relatively unhindered and without alpha protons. So here is another cross aldehyde reaction, but this formaldehyde have no alpha proton. So therefore, we only have one possible aldehyde addition. That means we can only have this addition. And we can only use this, the enolate from this aldehyde. Cross aldehyde reactions are only practical if the number of products can be minimized, which is achieved in one of the two ways. So one of the substrates is relatively unhindered and without alpha proton. And here is another example of those substrate is relatively unhindered and no alpha carbon. So this benzaldehyde. And again, this benzaldehyde will be attacked by this, the enolate from this aldehyde. because this has alpha carbon and has alpha hydrogen, and that the first aldehyde don't have like alpha hydrogen. This is possible when only one compound can form an enolate. In this case, this can form the enolate, and other compound react with enolate faster. The second way to perform a useful cross-aldehyde reaction is using LDA as a base. So this is called the directed aldehyde addition. We can use LDA to first produce the enolate. Once the enolate is produced, then we add in the second substrate. So one common compound is completely converted to enolate with LDA. The other carbonyl compound is then slowly added to the enolate. There is also possible the intramolecular aldehyde reaction to produce a cyclic compound. Here is one compound have two carbonyl diketone. So when we treat it with base at heat, we can produce this cyclic structure has 5 atoms. One group will form an enolate that attack the other group. So in this example, we can think of this alpha carbon produce the enolate, and then this enolate attack this carbonyl carbon, and we finally produce this 1, 2, 3, 4, 5 atom ring with this methyl, and then with this hydroxyl, and this hydroxyl this oxide get protonated, and we lost water to produce this CC double bond. Ester also undergo reversible condensation reaction. This type of reaction is called the Claisen condensation. Has ester under basic condition, and then work up with acid will produce this condensation product, which is the beta keto ester. So this is beta keto ester. Claisen condensation is simply a nucleophilic ester substitution reaction. Nucleophile is the enolate of an ester, and electrophile is an ester. Here is the mechanism. So the first step is proton transfer. Under basic condition, we can abstract one of the proton on the alpha carbon in this ester, produce this enolate. Enolate adds a nucleophile, attack the carbonyl carbon, produce alkoxide intermediate. Alkoxide reform the carbonyl, expel another alkoxide, and so then finally we remove this very active proton, produce this enolate, and then this enolate, the last step will be the we keep that enolate in that form to drive the reaction complete. So once the reaction complete, then we work up to regenerate to protonate this enolate to regenerate this final product. There are some limitations to the Claisen condensation. The starting ester must have 2 alpha protons because removal of the second proton by the alkoxide ion is what drives the equilibrium forward. Hydroxide cannot be used as the base to promote Claisen condensation, otherwise ester hydrolysis occurs. Here is an example of ester hydrolysis. The ester hydrolysis will produce alcohol and carboxylic acid after we protonate this oxide. So there are some limitations to the Claisen condensation and alkoxide that matching the OR group of ester is needed. Otherwise, trans-esterification occurs. So if we use, for example, here the ethoxide, and we use methoxide, and then we can see the trans-esterification. So your ester can be converted to a methyl ester. The cross-Claisen condensation are only useful if one of the following criteria is met. One ester has no alpha protons. Here again is one ester, no alpha proton. And this ester has alpha proton. Then we can have the cross-Claisen condensations. Or we perform the directed Claisen condensation with LDA as base. So starting with one ester using LDA to produce enolate, then we're adding another ester to finish the Claisen condensation. Intramolecular Claisen condensation can also be achieved called the Dieckmann cyclization. And here we have a molecule have two ester, and under basic condition, then work up at acidic condition, we can produce this cyclic structure. Like with Aldol reaction, Dieckmann cyclization prefer the formation of 5 to 6 membranes. The alpha position can be alkylated when the enolate is treated with alkyl halide. So in this example, we have this cyclic ketone. We treat with LDA to produce enolate. Then we can add in alkyl halide to adding the alkyl group on the alpha carbon. The enolate attack the alkyl halide via SN2 reaction. When you see SN2 reaction, that means when secondary or tertiary alkyl halide use, elimination will dominate. The Aldol reaction also compete with the desired alkylation, so a strong base such as LD must be used. Reduce selectively is an issue with unsymmetrical ketone. Two different enolates can form. Reduce selectively is an issue with unsymmetrical ketone. Two different enolates can form. And here is one example. We have this cyclic ketone use base to produce enolate, can be either the double bond on the right of the carbonyl on the left. And the one that is more substituted is more stable. The less substituted, the less stable, but forms faster. So therefore, we have the so-called dynamic enolate, more substituted, and kinetic enolate, less substituted. The kinetic and thermodynamic pathway, we will see these two pathways, starting with the same material, treated with base, and see the enolate. So the red approach produces less substituted enolate, which is a kinetic enolate, produces faster but not stable because the energy of this enolate is high. The more substituted enolate can produce slower because the activation energy for the blue line is higher, but the product of the product with the enolate is more stable. Kinetic enolate favored by irreversible conditions using LDA at lower temperature. Thermodynamic enolate favored by reversible conditions using room temperature. Using NaH at room temperature. So here are the two approaches. One approach is using relative high temperature, then we'll see the more substituted alkylation is produced. On the lower temperature, so the kinetic enolate is produced, and then we see the less substituted alkylation occurs on the left side of the molecule. The malonic ester synthesis is this process. So alkyl halide is converted into carboxylic acid with two additional carbons, and these OR reactions. That happens with diester malonate is the starting material. It is first reacted with a base to form a corresponding enolate. And here is one example of diester malonate. So diester malonate has this alpha hydrogen. So the alpha hydrogen is removed by ethyl side to produce this enolate, which is stabilized by the resonance structure, which means the negative charge is delocalized over all the 5 atoms. Then the enolate is reacted with L-pure halide. So enolate will be the nucleophile attack the L-pure group, then L-pure group will add on to this alpha carbon. Those ester group are then hydrolyzed, so that those ester group are hydrolyzed to recover the to convert both of them into the carboxylic acid. One of the resulting carboxylic acid group is then decarboxylated with heat. So one of them is lost as CO2. Once we dicarboxylic acid undergo decarboxylation in a parasitic process. So here is the kind of the mechanism. This pericyclic process. See those red arrow tell you the electron transfers. And so the proton was converted into that from this inner. And then we will produce another double bond here. And this electron transfer to that to produce the double bond. And then we see this loss of this CO2. We produce this inner tautomerized to produce the final carboxylic acid. The malonic ester synthesis overall is shown in this reaction. We started with diester malonate treated with the 3-step, and so we will see this product. Diester malonate can also be dialkylated, which means we keep adding the alkyl group on the alpha carbon, and then we heat on the acidic condition, lost one of the carboxyl group as CO2, and then the other ester group are hydrolyzed to acid. So another similar reaction is the acetic ester synthesis is analogous to the malonate synthesis. Convert an alkyl halide to methyl ketone with 3 new carbon atoms. So here is the acetic acid. Acetic ester, and go through this 3-step and added 3 carbons. Recall that alpha beta unsaturated carbonyl are made via aldol condensations. The alpha beta unsaturated carbonyl has 3 resonance contributors. We have this alpha beta unsaturated carbonyl, and we have those resonance structures. So starting from this, we can have these 2 small structures. Alpha beta unsaturated carbonyl have 3 resonance structure here. The beta carbon and the carbonyl carbon are electrophilic. So either we can think of this carbonyl carbon is electrophilic, and this carbon is electrophilic. So therefore, either carbon can be attacked depending on the nucleophile used. The result is the so-called the 1,2 addition and the 1,4 addition. And the Grignard reagent generally attack the carbonyl position. So this will be the 1,2 addition. Grignard number is alkyl magnesium bromide. So the Grignard reagent usually attack the carbonyl carbon. The Gilman reagent usually attack the beta position, and this will called the 1,4 addition or the conjugated addition. And here is one example of the Gilman reagent of the alkyl copper lithium, cuprate lithium. General mechanism for the conjugated addition is we started with nucleophile attack that beta carbon, And then we have this enolate protonatate produce enol tautomerize to produce the final carbonyl group. Stronger nucleophile tends towards 1,2 addition, less reactive nucleophile tend to do conjugated addition. Conjugated addition is 1,4 addition. Typical enolate often give a mixture of 1,2 and 1,4 addition. Stabilized enolate give 1,4 addition exclusively. So here is one example of 1,4 addition, and we have this. So this the diketone and this alpha beta unsaturated with the carbonyl, and we will have this 1,4 addition. So this alpha carbon here will acting as a nucleophile, attack this carbon here, produce this product. Right, so this conjugated 1,4 addition is called the Michael reaction. And we'll see the Michael donor nucleophile that does conjugated addition. Michael acceptor will be the alpha beta unsaturated with the carbonyl. So here is our Michael donor, and this will be our Michael acceptor. The following Michael donor give exclusively 1,4 addition with unsaturated carbonyl compound. List of common Michael donor and Michael acceptor. Michael donors and Michael acceptors. Acceptors are those alpha beta unsaturated carbonyl. Maybe aldehyde, maybe ketone, ester, nitrile, amide. And then here are those Michael donors. Because singly stabilized enolates do not give high yield Michael addition, Gilbert Stark developed a synthesis using an enemy intermediate. Recall how an enemy is made with a ketone and some of those amines produce enemy. Enemy behave like enolate. We are nucleophile. And this is enolate comparable with enemy. But an enemy is less nucleophilic and is a Michael donor. So after conjugated addition, use the enemy as nucleophile attack some of those alpha beta unsaturated with the carbonyl. And we initially produce this iminium and enolate, and they can both be hydrolyzed under acidic condition to avoid carbonyl and carbonyl. So the overall three-part process is a Stark enemy synthesis. We start with a carbonyl ketone and converting that into enemy, then adding the Michael acceptor, then which is alpha beta unsaturated carbonyl to produce the product. So the three steps is the first formation of enemy, Michael addition, then hydrolysis. Robinson annulation is a two-step process for forming a ring. Specifically, will be first Michael addition followed by two intramolecular aldehyde condensations. Let's see this, starting with this Michael addition, and so here will be this carbonyl carbon can have like one more proton, produce enolate, attack this carbon, produce this Michael product, and then the final step will be the intramolecular aldehyde reactions, aldehyde condensations. Right, so this means this alpha carbon here, okay, become enolate, attack this carbonyl carbon, and you will have a hydroxyl group here, then dehydration to produce this double bond. Most of the reactions in this chapter are C-C bond forming and yielding products that contain two functional groups, aldehyde reaction or condensation, Claisen condensation, stachyl-amine synthesis, microreaction. The position of the functional group in the target compound dictates what reaction can be used to synthesize it. So the stachyl-amine synthesis is 1,5-dicarbonyl compound, aldehyde and Claisen 1,3-difunctional compound. The different methods of error correlation. We have learned two methods of error correlation: the alpha position of inulator attacking an alkyl halide, a microdonor attacking a beta position of the microacceptor. These two reactions can be combined. The alpha halogenation of ketone, and we see here. So the carboxylic acid can also be halogenated by using a special process called the Hale-Wilhite-Zelinsky reactions. There are two steps. The alpha halogenation, haloform formation. So sometimes you can converting all the three here by Br, and then that become a butadiene group with converting the compound into an acid. Aldehyde addition and condensation, again, we can have the same compound or can cross aldehyde reactions. So the first, just the same carbonyl compound and go through the process either lower temperature or heat, maybe produce the aldehyde addition product or the condensation product. When we want to have the cross aldehyde reaction, we must use one of the carbonyl compound that don't have alpha hydrogen, or we can, in this example, so this formaldehyde don't have alpha hydrogen, then we can have a simple one product. Or we have to use LDA, some strong base to directing the reaction into only one possible product. We also learned the intramolecular aldehyde condensation to produce a 5-member or 6-member ring. So we can use some of the compound has 2 carbonyl. If we can possibly produce a 5-atom ring or 6-atom ring, they will do that using the aldehyde condensations. Claisen condensation is about those condensation, very similar as aldehyde, but use esters. And there's also intramolecular Claisen condensation, also known as or called Dieckmann cyclization. And again, you want to produce at least 5-atom ring or 6-atom ring, less or more, or not stable. And we also can have the cross Claisen condensations, ester with ester. And again, you want to direct or one ester don't have the alpha hydrogen. In this example, this red ester don't have the alpha hydrogen. Error correlation, we are inulate. We have the symmetrical and non-symmetrical. And this is non-symmetrical. Then we have the kinetic control, which is this one. Kinetic control can happen at a lower temperature. We produce this error correlation on this less substituted alpha carbon. So these two alpha carbon, this one more substituted, this is less substituted. Depending on the reaction temperature, we can put an alkyl group on the less one or on the more substituted one. If you use high temperature, you can put the alkyl group on the more substituted. At lower temperature, we'll put on the R group, the red one, on the less substituted. And we also learned the malonic ester synthesis. we can adding 2 carbon onto some of those alkyl group R here by using this like ethyl malonate. Another process of adding carbon to your alkyl group R is using the acetic ester. So that will add 3 carbons onto the R group here in this step 2, the RBR. Micro addition stabilize the carbon nucleophile, so we can see the micro addition like that. So we can use those Gilman reagents and adding the R onto the beta carbon, and we can also use the so-called micro donor, micro acceptor. We can also adding, this factor which can be converted into the enolate, and the enolate is stabilized, so that become a nucleophile attack this beta carbon and produce this product. And then some process you can do is using the Stark enemy synthesis. So we can convert the carbonyl into an enemy. The enemy acting as micro donor to attack the beta carbon to produce a product like that. The Robinson annulation has like 2 steps. So we first do like a micro addition, so micro donor, micro acceptor, and then we will see the intramolecular aldehyde condensation to produce this condensed double bond. Okay, so this is the end of this chapter 21.